screen தெரியுதா PPT?
தெரியுது சார். தெரியுது சார்.
Shall we start the class? I think maybe 1 or 2 minutes. I see only 18 students.
Sir, just 2 minutes, sir. Myself.
Yeah, we'll wait for 2 minutes. No issue.
Yes, sir.
So where did you stop in the previous class? Can I have some idea? We started the induction motor, correct? Anything can you say where we stopped? Any idea? Would be easy.
Last slide.
Induction motor.
Induction motor only, sir.
What did we talk?
Wait a minute. Just a minute.
Problem.
Rotating magnetic field we talk? No?
Sir, we talked about the transformer ratio and we did one example.
I just talked about transformer. Okay, the basic principle behind the induction motor. I just started about transformer, what is transformer ratio, and yeah, I remember. Thank you. Nice. Okay.
Sir?
Yeah.
Sir, just one suggestion, sir. Suggestion and request, sir. Right now, we have completed around 14 classes as of now. So, sir, for a midterm syllabus, can we consider midterm syllabus? Midterm is around or midsum, sir. Midsum we are planned to have on 23rd of March.
Yeah,
sir.
23rd March, correct. So 23rd March, whatever will cover up to 19.
March 12th, March 12th, we are in this same planned manner, we will reach around 23 classes, sir.
Yeah.
24 classes. March 12th will be the better for us, sir.
Yeah, March 25th. Okay, we will stop at March 25th, but the exam will be on 20.
No, sir. March 12th, sir. March 12th.
Upcoming 2 weeks.
Sir, from today, another 9 classes are there. Already 14 or 15 hours we have taken. So it will be around some 24 classes will be 24 hours.
Okay, no issue. Okay, we can.
Up to March 12th, we can consider for the syllabus. Then it will be more than half a mark of the syllabus, sir. That is what.
Yeah. Okay. We can do that. Okay. Fine. Okay. We'll start the class. Okay.
Thank you, sir.
I talked about transformer. Why? Because induction motor works based on the principle of transformer only. Now today we'll jump start into the induction motor, how it works, how problem solving, all those things. Okay, when we talk about inductor motor, since the transformer also works based on the principle of induction. In primary coil, we are giving a AC voltage. It produces a varying magnetic field in the transformer core, which will be cut by the secondary coil of the transformer. So there's a voltage induced. Already I told you the voltage induced in the secondary is equal to primary voltage multiplied by the transformer ratio. Transformer ratio is nothing but number of secondary coils divided by primary coils. Same principle is used in induction motor also. That's why it's called induction motor. Okay. We are supplying, in case of synchronous motor, DC motor, we have primary the field coil and armature coil. Both you need to supply DC voltage in case of DC motor. In case of AC synchronous motor, which we saw in previous 2 or 3 classes, the primary coil is supplied 3-phase AC voltage, and the rotor is supplied the DC voltage. So there's a DC magnet. It can have a permanent magnet. Later we are going to see the permanent magnet DC motor, a synchronous DC motor, PM SM, correct? Permanent magnet synchronous motor. We saw regular synchronous motor, in which the rotor also is an electromagnet, but you are supplying the DC voltage. that magnet, DC magnet will have constant magnetic polarity, north and south. That will be get locked with the rotating magnetic field of the stator magnetic field, and that's why the motor is rotating. So there are two power supply: one AC power supply for stator, one DC power supply for rotor. In case synchronous, but in case of synchronous motor, only one input voltage will be giving. For the rotor, there will be a coil. That coil, in the coil, there will be induced voltage because of the stator voltage. Stator works as a primary coil, a primary of the transformer, similar to this one, in which we are supplying voltage. There's a current flow. There are three-phase rotating magnetic fields similar to synchronous motor. That magnetic flux will be cut by the rotor coils, and there will be voltage induced in the rotor. That voltage, because of that voltage, there will be a current flowing in the rotor. That current produces a magnetic field. That magnetic field interacts with the stator field, and the motor start working. So that's why we call it induction motor. So induction motor, there are two type of induction motor. Okay, please take the notes. One is called as squirrel cage type. Other one is called wound rotor with slip ring. Please see that induction motor has two parts. One is a stator winding and rotor winding. Okay, this rotor winding can be these two things. One is squirrel cage type, other one is called wound rotor type. That's why the motor itself classified as squirrel cage type motor, wound rotor type. Please note that this is based on classification of rotor winding, how the rotor is winding, the connections, all this in rotor. But as per stator is concerned, it is same. There's a three-phase stator winding. The three-phase stator winding will be supplied with three-phase AC voltage. The rotor, no supply voltage, note down. In rotor, only induced voltage is created. Induced voltage is generated due to stator magnetic field. Right? The stator magnetic field is due to, we are supplying three-phase, there is a rotating magnetic field. Magnetic, I can say rotating stator magnetic field. Again, please note that it is similar to synchronous motor. Synchronous motor, you have a three-phase coil. In case of a three-phase motor, then you are supplying three-phase AC voltage. That voltage generates a three-phase rotating magnetic field in the stator windings. That will be cut by the stator the rotor windings. The rotor winding cuts this rotating magnetic field. So there is an induced voltage due to magnetic field, stator magnetic field in the rotor coil, correct? Rotor winding. So that voltage, due to voltage, there will be a current flow. Rotor current. So rotor magnetic field. So this rotor will interacts with the stator magnetic field, similar to synchronous motor, it works. So that means induction motor classification two type. One is called squirrel cage type. Other one is wound rotor type. Very popular is squirrel cage type. We'll see. Very popular is squirrel cage type because of advantage compared to wound rotor. But some application you may use wound rotor also. Okay. Noted down. I will go to next slide. Okay. When we talk about this induction motor, the basic principle is it works on Faraday's law. Faraday's law of EMF induction. Correct? We know that the similar to transformer. transformer also, you are supplying voltage to primary coil. Here, the stator coil works as a primary coil. Secondly, you are not supplying the voltage induced because of the magnetic field created. That voltage can be supplied to any load. As I told you, we can do same thing. Only here it works on this one. And another thing, Faraday's law, already I told you, Lenz law also. Direction of magnetic field, all this thing controlled by Lenz. These are the two laws. According to that, when stator is supplied with an AC voltage, then the voltage induced rotor, we call that, I can say that, for example, take a single coil, but there are three-phase coil. But here we say V rotor voltage. V rotor is nothing but minus N into d by dt of phi. Correct? I can say the phi stator. S means stator magnetic flux. Correct? We know the three coils. You, for understanding, you take one coil similar to transformer. I can say this is in transformer, we call pi P. Correct? Primary magnetic flux. We supply Vp because of the IP. This is primary voltage. This is primary current. Correct? This is primary magnetic flux. Correct? This happens in the transfer. Same thing only here also. Because of this, there's a secondary voltage Vs. Vs equal to transformer ratio times Vp. Already we know that. And Is will be there. Is equal to Vs divided by Z. Z is called as impedance of the, I can say Zs. Secondary coil. Already I told you what is Z. Impedance equal to R square plus XL square root. Because coil has resistance, because it is made of resistive copper, aluminum, some material. Also it has inductance, and 2 pi FL is the XL. That is inductive reactance. If you put R square this one, we will compute the impedance. Z is called impedance. Impedance voltage divided by the which voltage? Secondary voltage, induced voltage in the secondary coil divided by Z will give secondary this one. Because of that, phi S will be there. Correct? So please know that because of phi S only, this voltage is induced. Correct? In the transformer, the primary magnetic flux induces a voltage, and when current flows, there will be a flux, magnetic flux in secondary coil also. That correct? But since nothing is moving there, we ignore this. Voltage is due to the primary coil. So similar to here, stator magnetic flux is varying. Please note that voltage, induced voltage in any coil will happen only when there is a change in magnetic flux. Okay, so that means you can have a constant magnetic flux, something like this. Correct? I say the phi from, for example, north pole to south pole. I have a magnet. Correct? North and south pole is there. That means between this, there's a magnetic flux. So this is a constant magnetic flux. Phi is constant. Now, I take a coil. Correct? Already we talked many times. I take a wire having some length. Correct? And the wire is moving like this, diagonally, cutting across the magnetic flux. Then there'll be a voltage. Correct? VEMF. Voltage generated equal to minus N multiplied by d by dt of phi, where phi is the magnetic flux. That means only when there is a change in magnetic flux, the flux are constant in this case, but my wire is moving. If that means it is cutting, there will be a change in magnetic flux. This is what the generator principle. Similar to that, otherwise, also it is possible to generate voltage if magnetic flux itself is varying. Correct? So in the magnetic flux itself varying, in case of AC motors, we know that I am supplying a AC voltage to the stator winding. Correct? Stator winding voltage is varying 0 to Vmax, plus Vmax, and it is coming minus Vmax. The change in 0 volts or like that goes. This is for example 100 volts. Again, it comes to 0. That means the voltage is varying. Because of that, there will be a current flowing in the because of voltage, the current also is varying with respect to time. Red one is current. If it is varying, in the varying magnetic field, if I put a wire, correct? I put a wire, correct? So then because of this, magnetic flux also happens. Happens a magnetic flux also varying similarly. This is my phi, this is my I. Now in this I put a wire, correct? Yeah, wire, correct, is there. This is a wire. Automatically a voltage will be induced. Because why? The current is varying from 0. I say that this is 10 Tesla. Tesla is a very big number. Okay, for understanding purpose, correct? So 0, 2, 3, this is 5, 6, 7, 10. Again, it decreases. You can say that the magnetic flux value is varying. So automatically d by dt of flux is happening. Now my wire is not moving. Even that's what happened in the transformer. Secondary is not moving, primary is not moving, but the magnetic flux generated by pi p, correct, in this one is varying with respect to time. That is as good as creating varying d by dt of phi. That is due to AC voltage supply. That's why there's a secondary voltage induced. Same thing it happens in induction motor also. In induction motors, stator we are giving AC voltage because of there is a stator current is varying. I said that this is stator voltage. This is the stator magnetic flux. So the rotor has a coil, but we are not supplying voltage. There is induced voltage. Because of that, the voltage induced, a current flows in the rotor. Because of the magnetic flux is created, that magnetic flux interacts with the rotating magnetic flux stator. Automatically, the torque is generated. The motor start moving. And if you connect a load, it can take the load. Correct? This is the basic principle of the induction motor. Okay. Now, since already we talked about. Okay, so now I show what will be internal structure, correct? Take down this picture. In the exam, you are expected to draw 3 hand drawing only. You can roughly draw, okay? If there are 2 parts, I told you, one is called as stator winding, other one is called rotor winding. First, let me explain the stator winding. I am talking about 3-phase motor, correct? 3-phase motor, you can see that this shows a cross-section view of 3-phase induction motor stator part alone, okay? So, there are 3 coils R, G, B, correct? For the 3 coils, I am giving 3-phase input voltage, 3-phase AC voltage, correct? You show me 3 receivers, it is sinusoidal varying, and each coil is separated by 120 degree apart. So the voltage also separated by 120 degree in phase, correct? AC voltage applied through phase is this one, red phase, green phase, blue phase, and you can see that there are 6 stator poles, correct? This is red, correct? Red R dash, correct? I can R dash. This is blue, opposite pole B dash. Then I say that green dash. So together, this plus this is called one magnetic pair, and this is another magnetic pole pair, and this is another pole pair. So there are 6 poles. Diagonal opposite poles are wound with same coil, correct? 3-phase coil. One is red coil. You can see the red is, this is input voltage. I'm giving this input voltage. Current flow through this coil, through this fold, then comes like this. You can see that and enters here and this go to neutral. Correct? In 3-phase, all the voltage will start from the particular phase, R phase, green phase, blue phase, finally end up neutral wire, which is like a ground. So the current from R phase enters to this one. So this will become north pole. You can say that this is opposite south pole. Okay. For the blue, the current enters here. This will be north. This will be south. So green, the current enters here. This is north. This is south. This is called per pole pair. So that means 3 pole pairs or 6 poles are there. Okay, each is supplied with one phase voltage, R phase voltage, green phase, G, RGB. They are supplied 120 degree. So because we are supplying this, you can see that these three coil sets with this voltage produces a rotating three-phase magnetic field similar to synchronous motor. So this shows these arrows, blue color arrow, red color arrow, green color arrow, shows the magnetic field vector, correct? It shows magnetic field vector at given instant, correct? So with respect to this is called 0 degree, I can say that this is 30 degree, correct? This is 180. So this is 60, correct? This is 120, 180, correct? 0, 60, 120, 180, like that. Up to 720 degree is, 360 degree is one cycle, correct? We say that 0 to 360 degrees, one cycle. Within the time, all three phases will be go to maximum minimum voltage. Because of that, this we know that being a vector, the length of the vector decide what is the magnitude of the magnetic. This one. So you can see that the R and blue phases has some magnet. This is phi B. This is phi R. This is phi G. That means magnetic field due to green phase. Okay, voltage. This is magnetic to blue phase. This is magnetic one. At this particular instant, correct? At the time instant means we are talking about this is any instant. You can take any instant, correct? You can take any instant. At that instant, the magnetic flux on three phases are like this. So you can see that predominantly the green phase has maximum magnetic flux compared to other two. The resultant magnetic force generated will be in this direction. Okay, as this rotates, I am going to show that as the voltage is varying from 0 to 360, this vector will rotate like this. Okay, sir. The vector will have different this one. Next, this may be 1 minute. I may select a proper color. Next instant, this is this one. And in another instant, I am talking. Green is like this. And you can see that the voltage, red phase voltage is peaking, correct? For example, you take this instant. At this instant, this is the maximum voltage. Red phase has the maximum voltage. At that instant, if you bring it down, you can see that this blue and green, they are negative voltage. This is 0 volts. This is negative volts. This is positive, correct? At this time instant, at this one, 360 degree, you can see that this has maximum voltage. Red phase has a maximum voltage. Other two are negative, but still minus, correct? Not the maximum voltage. That means the resultant to this one is red is maximum, correct? So that means the rod will be attracted towards red phase. Okay, I will show in the next this one how it works. So you can, so this is how rotating magnetic, because the voltage is increasing, correct? Red is increasing, decreasing. When this is maximum, red is maximum, green and blue are minimum, not even 0, and negative is negative voltage. At this instant, if you see that green and red are positive, but they are equal, blue is negative maximum, correct? So that means resultant vector, the magnetic field vector will be towards the green phase. Okay, like that it happens. That is how the rotating magnetic fields are this one. Take this picture, correct? So induction motor, stator with the three-phase voltage we are giving like this. So these are the different pole pieces are there. R, G, B, coils, stator windings are wound over diagonal opposite phase and supplied with this one. So this gives. Okay. Then I said the next important part, induction motor, rotor. Induction motor, rotor. Rotor, there are two types. One is called wound rotor with a slip ring type rotor. Other one is called squirrel cage type, this one. You know the squirrel is a animal, no? Small animal, we will see squirrel, correct? So if you see the nest of the squirrel, It will not make, it takes whatever materials, correct? Like coconut tree, coconut shell, correct? The kaya, correct? Kaya, like that material will take, and it will make something like this. Not properly. It won't, like, say, you see the weaver bird, correct? Weaver bird make a very good nest hanging in the tree, something like this, correct? Taking the fibers, natural fibers, this is the entrance, it will be hanging. Many birds do nice nest, but squirrel cannot make proper nest. It also need nest. The construct a net, something like this, correct? Making material inside the detail, but it's not woven properly. So this one looks similar to a squirrel cage. Some electrical engineer given the name. Now it is stuck to that, you can't change. You can see that there are two things. In the rotor also, you need the coils, correct? Only thing is you are not supplying any voltage to the rotor coils. So you can see that in wound rotor, you have the rotor core, correct? Rotor core is shown in gray color with the slots. These are the slots. You can see the slots are going empty space, correct? In which the coils, correct? The rotor coils are wound inside that. You can fill inside the gap and coming out, correct? And then the end of the rotor coils are connected to a slip ring, correct? It is connected to slip ring, and through the slip ring, the rotor coil ends can be brought out. That is in slip ring type, that is the main thing. In slip ring type rotor, you have a rotor made of magnetic core material, generally iron plus nickel, all those things, this one, which has a slots. In the slots, you put the rotor coil, correct? These are the wound rotor coils, and they are inserted. The ends are brought up to the slip ring through which the connection is come out. And next slide, you'll show how you'll understand. But in case of squirrel cage, there's no coils. Instead of that, you can see that this is the shaft, because the rotor is a rotating part, correct? So you are going to put a bearing here, support bearing, other end also. So then you can connect your load. Wire is the shaft is coming out. Okay, same thing here. This is the shaft on which there is a, this is called a end ring, correct? You can see the end ring both sides. This is one end ring, this is one, and end ring have holes, correct? So end rings are also made of the conducting material. End rings also made of conducting bar, a circular ring with a thickness, correct? This you can a circular plate with thickness, but please see here. Here there's an insulator, correct? There's an insulator here which is prevents this conducting slip ring to be connected to shaft, correct? So similarly, there's this one. So then there are two end rings, solid end rings, which is connected by a conducting bars, correct? It can be made of copper or aluminum, correct? Instead of using winding wires, they use thick bars, correct? Thick, but these are the conducting bar. You can see here, this is conducting bar, this is conducting bar. They are connected to end. They are braced here, correct? Braced with the end rings of the squirrel cage type rotor, correct? No coils. Coils are replaced by conducting bars, and the conducting bars are connected by again another conducting end rings. That is all solving. So now, if magnetic flux cuts, correct? I have my stator coil outside, correct? This is my stator coil, correct? Here also, I have a stator coil. For example, at the stator coil, you are supplying AC voltage, correct? There's a 5 stator magnetic flux is created, something like this, and that cuts this wire. So there's a voltage, correct? Rotor voltage is induced. I say VR, where in this coil, same thing, stator AC voltage is supplied to this, correct? So 5 stator voltage generated, this magnetic flux. Please note that the magnetic flux created in this stator winding, correct? This I call a 5S, cuts this stator bar, conducting bar, because magnetic flux, but please note that it is a time varying magnetic flux. Phi E, S is varying with respect to both the case, whether it is a wound rotor or this one. the stator is supplied with three-phase AC voltage, three-phase rotating magnet, which is varying with respect. That means d by dt of phi is happening. Correct? Because magnetic flux itself varying, because voltage is varying, all these things. So because of this is cut by this bar, there's a voltage induced in rotor coil. Correct? Please note that here coil is nothing but a magnetic, but thick magnet, because being very steady, that is one of the advantage of screw-gated motor. Very rugged. Correct? It is not wire easily get corroded or copper, all those things. It generally be thick bars, maybe rectangular or round type bars, which is connected by the two end rings. This is what acts as a coil. This is the rotor coil. Correct? Here you have the both there's an induced voltage. Okay. Since induced voltage is generated, automatically there will be a current flow. Correct? I say that V rotor, I rotor, there are 5 rotor magnetic fields. Same thing happened here. V rotor, I rotor, 5 rotor is induced in the, whether it is a squirrel cage type or wound rotor, it happens. I'm going to explain what is the advantage. This and this. There are some advantages. So there we'll discuss. Okay. So both. So now there's a magnetic flux is created in the rotor. In both the case, this magnetic field going to interact with stator magnetic field and get locked, similar to synchronous motor, and this rotor start rotating along with synchronous. Okay, similar to synchronous motor. Any doubts? Okay, no doubts. Okay, now I showed the physical how it will look. Correct? The rotor windings, rotor and rotor, how it look in physical. This one, this is the image. Correct? But equivalent circuit, when the circuit is represented, if it is a slip ring type wound rotor based IM induction motor, means please take down this schematic diagram, circuit diagram. You have 3-phase stator coil. That means this is one phase 1, 2, 3, and each is supplied with RGB 3-phase AC voltage. This is stator coil. Correct? This is the stator coil connected. This is called a delta connection. There is another type called star connection. Correct? Yeah. Star connection is this. Correct? This is called delta connection. You know the delta symbol in Greek letter? Correct? This is delta letter in Greek symbol. Correct? So it looks like a triangle. So this if you connect, it look, the connection is with all 3-phase connected. So it is called delta connection. Okay. Similarly, this the rotor coil. This is a 3-phase rotor coil. Okay. In which you can see that there are 3 coils. They are connected like a star. Correct? Star generally we show something like this. Correct? We symbolically we show star with like this also. Correct? Sometimes we show like this. 5, 6 star. Generally symbolically represent star is like. So since the connection looks like a star, correct? This is star connection. Rotor coil is connected as a star connection. Correct? Stator is a delta connection. But you can see that. Okay. You have a rotor, 3-phase rotor. I supply RGB voltage. So there will be, I say VR, VG, VB. There will be IR, current flowing, IG, and IB, 3-phase. Because of that, there's a 3-phase rotating magnetic field created by this, which is going to rotate at synchronous speed. The magnetic field of stator will rotate at synchronous speed, similar to synchronous motor, which is represent NS. NS equal to 2F divided by P. Correct? This is called as RPM, number of rotations per second. Otherwise, we can write 120 F divided by P. Already we know that. When we talk of synchronous, note down this formula. Same as synchronous motor, induction motor also, rotating magnetic field created stator winding due to 3-phase input voltage, AC voltages can be calculated NS equal to, this is revolution per second or revolution per minute, RPM. Generally, we talk RPM, not RPS. Sometimes some books they may mention RPS also. It is nothing but 2F into P. We know that P, what is P? P is number of poles. Correct? Number of poles, but the previous this one, how many poles we have? P equals 6 poles. Correct? And if you supply F, supply frequency F in India equal to 50 hertz. So automatically NS in India for a 6-pole induction motor, what I showed in previous, correct? This one, NS is going to be 120 into 50 divided by 6. Okay, so it is going to be, we know that this is going to be 2 equal to okay, so many RPM. So you can calculate the speed of synchronous rotating magnetic synchronous speed. This is the magnetic field rotation. This is what going to design the speed of the rotor. Okay. So now this shows figure of the slip ring to wound rotor. You have 3-phase stator coil. This is the rotor coil. But only one thing is you can see that the rotor coil ends are brought out to a external resistance. You can see that this is very important. Note down. An external resistor, which is a variable resistance. This is symbol for a variable resistance. If I put it like this, I know that you know that this is R, symbol for fixed resistance. We call it as fixed resistance. Correct? R equal to 100 ohms. If I show like this is called a variable resistance. Because there are 3 pins of 1, 2, 3. So this is called a variable resistance, which is also called a rheostat. You would have gone in the physics lab, you would have used, or somewhere electrical lab, you would have used rheostat. Is connected to a rheostat. 3 rheostat are connected together, and the coil ends, rotor coil ends are connected to the external resistors, 3 rheostats. So we know that, yes, please. Hello, somebody asking some questions. Okay, so we know that coil means it is made of copper wire, correct? So the rotor, I will say that this also has rotor resistance R subscript, correct? All 3 phases, this one. So this has resistance plus inductance, correct? LR, this also plus LR, this also plus LR. Inductance of the coil. This coil has resistance for inductance. So apart from this resistance, I am adding external resistance. And to add this one, being a rotating part, rotor is a rotating part. So how will you connect external resistance? You cannot directly connect through a direct wire. Then the wire will get twisted when the rotor is rotating. So I have a slip ring. This is the slip ring arrangement. That's what I said. Slip ring arrangement. The ends of the one end of the all 3 coil are connected shorted. Correct? Because this is one end, second end. One end, second end, first end, second end. The first ends are all these are connected shorted. The second end of 3 rotor coils in slip ring to wound rotor is brought out through a slip ring mechanism which is attached to the motor shaft so that the external resistor can be connected. This we are going to see what is the advantage later. Correct? The external resistance helps in increasing the torque of the motor. If I want to change the rotor torque, correct, then I can vary the resistance of rotor coil. The rotor coil resistance plays an important role. If so, to increase or decrease, I am adding additional resistance. I said this is rotor coil already has some resistance each phase. Correct? It has a, for example, RR equal to say 1 ohm, or I say 2 ohm. Correct? I am adding another 2 ohms additionally. This resistance can be varied 0 to 2 ohms. That means I can add 0 to 2 ohms for each phase of the rotor coil. Correct? So by varying the sliding mechanism. So simultaneously varying all this thing, the rotor coil resistance of slip ring rotor can be varied from 2 to 4 ohms. Correct? When the slider is this end, this is 0 ohm. When slider goes to this end, it becomes 2 ohms. That means I can add 2 plus 0 to 2 ohms. So that means any given time, the each coil rotor resistance can be 2 to 4 ohms you can change. You cannot bring less than 2. So by varying the rotor resistance RR, I can increase the torque or control of the motor, type motor. But many times the induction motor is used for constant speed, fixed torque. In that case, there is no need to have this business. Please note that this has additional cost and mechanical additional cost and fabrication difficulties. Correct? You need to attach a slip ring. Slip ring will worn after few hours of few hundreds of hours, because the brushes, all those things get worn out, all these things complicates. Correct? But if I don't want to change my torque of the motor or speed of the motor by adding external resistor, I can go for what we call as a squirrel cage motor. So take down both, because please note down both. If your exam asks to draw the slip ring type, I am not going to ask you to draw this. There is no need, but you are expected to draw this and a part mentioning. So slip ring type turn, rotor coil, one end is shorter, other end is brought out to a slip ring and connected external resistor, and I can vary external resistor so that the rotor coil resistance can be increased or decreased from the original value. Correct? Original, this coil resistance cannot change. Already the coil is wound, it is inside the motor. Additionally, you can add now, if you think that your application doesn't require change of the speed or torque of the induction motor, then you can go for squirrel cage type motor. In squirrel cage type motor, already you know what I have. First of all, I don't have this coil, no slip ring. I have two end rings in which instead of having coil, thick bars are connected. Advantage of this bar is ruggedness. Correct? They won't go easily, but of course the thickness under the length of the this bars, all this thing depends on how much torque, how much current it has to flow, how much voltage into the length, all those things matter. Similar to coil only. The conducting bar acts as a coil, but only thing they are rugged and simple construction, very simple. And you can see the no slip ring. You are not bringing out anything external. It is everything is made. So because of that, it becomes now the equivalent circuit of the squirrel cage rotor. Again, you have three-phase voltage given to RGB phase to stator coil three-phase. Again, same delta connection. The rotor coil are connected. Bars, squirrel cage is connected in this one. Ends are shorted. Please note that this is end one of the one coil. 2, 1, 2, 1, 2. The one end of the first, all three coil are shorted, and other end of the coil also shorted. What is the shorting? This is the end bars. Correct? You can say that here I call it end rings. Correct? So that is what this. What it does, it short circuits the coil. Coil is nothing bar. Here also it is short circuit. This is one end ring. This is the second end ring. Correct? This is sorted by second end ring. So you can see that the very simple. Nothing is brought out. Everything is self-contained in the motor. Advantage, very rugged construction. And but only thing, what is drawback? The R, rotor resistance R cannot be changed. Cannot be changed in squirrel cage type. So that means torque and speed of the squirrel cage motor you cannot change. That is fixed for given amount of input voltage. Correct? Vs, stator voltage. Correct? And stator coil 5S and RR and LR and number of turns of the rotor. Correct? So everything is fixed. So motor runs at constant speed. And what is the speed it can run? Maximum speed. Ns equal to 120 F divided by P. This is synchronous speed or magnetic field. So rotor speed called NR can be equal to Ns or less. Correct? The maximum speed, the motor shaft, which is that this motor shaft speed I call as NR, or sometimes I call it shaft speed. Correct? Shaft speed NR can be equal to synchronous speed of the rotating file, or it can be less only. Only two possibilities. We will see what it is later. Okay, when we are talking. So this is how the two types of synchronous motor, the induction motor rotors based on that classification. Squirrel cage type motor or slip ring wound rotor type motor. Okay, the circuit you note down, please. Now, I told we are going to generate rotating magnetic field, correct? So, how the rotating magnet? Please take this picture. In the exam, it is expected. Okay, so what we are giving is we are supplying three-phase AC voltage. Due to that, there is a three-phase current flowing in the stator winding coils, and due to that, there are three-phase magnetic flux created. One is pi r, that means red phase magnetic flux is varying in sinusoidal fashion. This is, you can see that x-axis is degrees, 0 degree. This is nothing but 0 degree. At 0 degree, red phase magnetic flux is 0, correct? And it is increasing sinusoidally. It goes. When it is 90 degree with respect to starting location, this is 90 degree. You can see red phase become maximum flux. Phi r magnetic flux created red phase is maximum. I say phi max. At the same time, at 0 degree, you can see that the red phase is 0, magnetic value phi r is 0. At that instant, you can see that blue phase is not 0. It is √3/2 times. This is phi max. This is √3 times phi max. You can see that voltage. The magnetic field is that time voltage. Similarly, at the same instant, green, correct? Phi g is also minus √3 times 2 phi max. Phi max, you consider all three phase can reach only this value, maximum, correct? You can RGB here, blue is max. You can see the blue is maximum, positive max, phi max, and this is negative phi max. And this is positive phi max, red phase, this is negative phi max. Okay, green phase, this is positive phi max, and here negative phi max. Correct? So all three phases can start from 0, correct? Start from 0, it can increases, go to maximum, comes to again 0, comes to negative, again. This is one cycle of red phase. Similarly, if I talk about the blue phase, this one, I can start from here, understanding purpose. This is 0, and it comes to blue, you can see the minus maximum, goes back 0, plus maximum, again it ends. So this is one cycle of red phase. Sorry, blue phase. Similarly, you can see that green phase also. I can say that you can take one cycle is one max to same, correct? I can say this is minus phi max and this is plus phi max, again minus. So this is one cycle, correct? 360 degree. All three phases are start from 0, goes to positive phi max, negative phi max, again 0. So, but they are separated by 120 degree apart, correct? Each one is separated by 120. This is 120 degree. This is also 120 degree. All three phases rotated. So, this is rotating magnetic field created in the stator winding by supplying three-phase AC voltage, RGB. Okay. Now, we can see that starting from 0 degree up to 360 degree. For your understanding, we have marked the resultant. This is called a resultant magnetic field. This angle. So this is the resultant magnetic field. You can see that at time instant 0 degree, correct? You can see that R phase equal to 0, magnetic field is 0, blue phase is positive, correct? √3/2 of phi max. Green is at minus √3/2 phi max. So this much magnetic flux is negative side. This is positive. Red phase magnetic is 0. So at this instant, the resultant magnetic field between there are two magnetic field acting. One is 0. The resultant direction of, because it is vectors. I told you these are vectors because resultant magnetic field is acting downwards. That is what shown in this picture. Correct? The resultant magnet is shown here. At this instant, at P1 instant, resultant magnetic field is rotating. Now, take at 60 degree. From 0 after 60 degree, you can see that I can mark like this. Correct? So, red one, now it becomes √3 plus √3 times 2 into pi max. Correct? You can see that in the x-axis, if I draw horizontal line, it cuts here. Correct? This is root 3 times 5 max. This location. This is root 3 times by 2 into 5 max. Of course, is negative. This value. This value is positive, this one. So you can see that the red phase magnifier reach root 3 times positive. That time blue is 0. Correct? You can see that 5 blue equal to 0. But the green is minus root 3 times to 5 max. Okay. So now the resultant vector will be like this. You can see that I am marking here, circling here. The resultant magnetic flux is, you can see that because the magnetic flux is rotating 360 degree. It can rotate 360 degree. So this is minus, correct? Minus 90 degree, correct? So this is negative side only 60 degree, correct? It is in 60 degree resultant, one phase. Now, if I talk about next one, at this instant P3, if I draw this pi g, it becomes 0, but phi r still root 3 times by 2 into 5 max. Blue still it is in the this one, correct? This is going to be root 3 times divided by 2 minus into 5 max. So the resultant vector is in this quarter. We know that 360, this is called first quadrant, second quadrant, third quadrant, fourth quadrant, correct? This total is 360 degree, correct? So you can see that the magnetic flux is rotating like this. It was here, then it rotated like this, then it rotated in this instant, further rotated, then it rotated 180 degree. In this rotation, it has rotated this much. In this rotation, it rotated this much. In the last, again come back to original position, correct? So within 360 degree, since the magnetic or red blue phase is varying, I have taken 7 instances. P1 at 0 degree, at 60 degree, 120 degree, 180 degree, 240, 300, 360. At that time, how the resultant. So this is the stator resultant magnetic flux. Correct? It is rotating like this. Correct? So this figure you are expected, right? Our rotating magnet, how it created is this figure you need to draw. Then how it is created, we are going to talk about that. Just another 5 minutes. I want to close this today. So next class we can look into some problems. So this is rotating magnetic flux we understood, and now the phi r, correct, red phase. We say that phi max, maximum value it can reach. Maximum value any phase reach can be phi max. It can positive direction, negative, only this much value. This is the value, correct? This is the maximum value it can reach, phi max. Okay. So the phi max multiplied by sine omega t. Because I am taking this a reference phase. R phase taken as a reference. So automatically phi g, green phase is going to be at that this one, phi sine omega t minus 120 degree with respect to this one. Phi b is going to be pi m into sine omega t minus 240. Correct? I am talking only this. At this instant, if you take this is 0 degree, and automatically with respect to that, each one is shifted by 120 degree. With respect to R phase, blue phase magnifier is separated by 120 degree spatially. Blue phase is rotated by 240. Correct? So this is the magnetic phase. So this can be drawn like this. At the time instant, I can draw something like this. correct? So this is phi R, this is phi G, this is phi B. Each one is separated by 120 degree. Please note that it is going to rotate. I am given at particular instant while taking a reference. Okay. Now, this is how the initial starting, correct? So we saw at this instant P1, P2, P3, P4, P5, P6, P7. I have computed the resultant phi R, small phi resultant, correct? I shown the vector, resultant magnetic flux is shown in arrows with some length, correct? This length decides this strength or magnitude of the resultant magnetic flux. This angle represents at what angle it is acting at that given instant after 360 degree, correct? So now how we got it only we are going to explain. At position, correct, P1, correct? That is omega t equal to 0 degree. Starting location, we know that phi r equal to 0, it field strength is 0. Please note that here field strength is 0. P1, red equal to 0. Okay. Blue equal to this much. That is plus root 3 by 2 into 5 max. Green equal to minus root 3 divided by 5 max. That's what I am going to, correct? So 5G is going to minus root 3 divided by 2 into 5 max. Blue is going to be root 3 divided by 2 into 5 max. Please see that this is plus, this is minus. Okay. These three are acting at omega at 0 degree, correct? At position P1. So what will be the resultant magnetic flux? Correct? Resultant magnetic flux, how will you complete? You have to draw vector diagram. Vector diagram. So okay. So this is root 3 by 2 pi max. This is also root 3 by 2 into 5 max. This is positive. This is negative. Okay. So there are two are. The one is 5G. Other one is, this is 5G. This is 5 blue. What about this one? R? Pi R equal to 0. So there's no role. At the time instant, phi R is 0. No role, only these two. So what is the result? This is my resultant magnetic field, phi R. Correct? So this can be connected by a parallelogram. Okay, this is the resultant. I can put small r because capital R means you will get confused with red face. So we need to use small r. Resultant magnetic flux is represented by phi res or phi R. Phi R is going to be this is A, this also A, correct? So this angle is equal to 60 degree. Okay, so now we can calculate, and this angle I call it alpha. Alpha equal to 60 degree. Then we can say that phi R equal to 2 into A. Parallelogram, one side is A, correct? There are two sides. That's why 2 into A into cos alpha divided by 2. We can write like this, 2 into this. This is nothing but 5 root 3 by 2. That is nothing but A is nothing but root 3 by 2 into cos alpha equal to 60 divided by 2. We substitute alpha is 60 and A equal to root 3 by 2. Because there are 2, that's why you multiply 2. So I can say that this can root 3 by 2 into 5 max into root 3 by 2. And so we can write 3 by 2 into 5 max is going to be 0.866. Note down, it is going to be 0.cc into 5 max. So the resultant magnetic flux, this is going to be I can say that 2 divided by 5 max is nothing but 0.866 into 5 max. Okay, so this is at this one. Similarly, I'll just few more minutes. I want to close this today. Similarly, if I take the next instant, time instant at position P2, please note that position I am referring here. Let me clear this. You will have a clear idea. This is P2. For P1, we compute a resultant. P2, P3, P4, like that we can compute. I will just give 4 examples so that we will be able to. At least on phi r equal to root 3 by 2 into 5 max, phi g equal to minus root 3 divided by 5 max. But you see phi b equal to 0. I'll go back to figure, you will understand. Correct? At this instant, P2, at the P2, correct? At P2, I extend a dotted line, you will understand. Correct? This is minus root 3 by 2. That is green phase. Okay? The red phase is plus root 3 by 2. Understand? Because it's catching on 0. That's what we are written here. Correct? At this one. So if I draw the parallel, this one, vector diagram for this time instant. So this is going to be root 3 time divided by 2 into 5 max. This is also minus root 3 time divided by 5 max. The resultant vector phi r, correct? Phi r is going to be like this. This can be connected by a parallelogram. Okay. So this is also going to be, the value is going to be, phi r is going to be 0.866 into 5 max. Okay. But you can see that the resultant vector, if I draw the 360 degree, this one. So 1 minute. Just I will complete today. I just want to do that. X and Y axis. Correct? You can see that the resultant vector is here in this direction. If you see the figure, correct? If you see the figure, you can see here angle with vector. Correct? So this is 0.866 times 5 max, but angle with respect to this is rotated by this much. Correct? It is rotated from here, it is rotated like this. So originally it was like this. Now that is this, correct? And it is rotated by 60 degree and it is like this with a strength of root 0.88, root 3 by 2 or 0.886 by 5 max. Okay. So same thing we can go ahead for other, this one also. For at position 3, I'll just take 2 minutes, I will complete. Okay. Position 3. Phi r equal to, please refer the figure, you will understand. 5 max, red phase, and phi g equal to 0. And phi b equal to minus root 3 divided by 2 into 5 max. Okay. So the vectors. Sorry, 1 minute. Okay. So this is phi r resultant vector, and this the phi r is going to be root 3 by 2. is going to 0.866 into 5 max. Okay. Similarly, at position 4, same thing. For your understanding, only quickly I will complete. Phi r equal to 0. Please refer the figure. Phi g equal to root 3 by 2 into 5 max, and phi b equal to minus root 3 divided by 2 into 5 max. Okay. So again, phi r is going to be 0.866 into 5 max. Okay. How the vector is going to be, this one will be something like this. This is phi r. Okay. And this is root 3 divided by 2 5 max. This is also root 3 divided by 2 into 5 max. This is a resultant vector. Okay. So I shown this one by looking at this figure. Correct. By looking at this figure, you can draw. Up to this one, I shown that for this instant also you can find out. Correct. So this is minus root 3 divided by 2 5 max. This green is plus root 3 divided by 2 5 max. Blue equal to 0. Correct. So like this, each dimension you can calculate, draw the vector diagram like as a parallelogram, and you can find out degrees also. So from this, what you can understand is the rotating magnetic field here, because I am giving a 3-phase voltage which is separated by 120 degree. Current also varies. So magnetic field created each phase also sinusoidal varying. Since finally all three are going to interact on the rotor. So this is the magnetic field going to work on the rotor, resultant magnetic flux, but it also rotates. Correct? It also rotates with respect. So by 360 degree, within 360 degree, it started minus 90 degree. Correct? Then it rotated like this, rotated. Finally, again came back to minus 90 degree. Correct? Here plus 90 degree. Correct? So it rotates. This is, you can see that. So this resultant magnetic field only going to induce a voltage in the rotor because of the current. That current interacts with the rotating magnet and the torque is produced and the rotor rotates. I stop here. Next week, we will talk about problem solving. How the equation, building the torque equation and equivalent circuit tomorrow. Correct? So we talk equivalent voltage, torque, current, equivalent circuit, and also how to control the motor, torque, all this you will see. See you tomorrow. Thank you very much. Please give a Ratnam before leaving.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Yeah.